Okay, so we are going to continue on this particle in a one-dimensional infinite potential well. Okay, the situation here is, like imagine if you have a bucket or well with an infinitely high wall, okay, and then, within the bucket or well, we are kind of placing a particle, or, like this particle can be also represented as wave, and then that one is within the bucket, okay? So for that, like we are trying to solve this problem, with the Schrödinger equation. So here, this is a time-independent Schrödinger equation written. And then we have to actually look at three different regimes, regime 1 and regime 2 and regime 3. And last time, we kind of argued that the psi or wave function, for regime 1 and regime 3, it has to be actually 0. And then the reason for that is because, when you consider this psi star psi, what is this psi star and psi? This is a probability density function, right? This is a probability of finding the matter at any location. So in the sense, what is the probability of finding this particle in regime 1 and regime 3? That must be 0, right? Because, you see infinitely high wall, what is the probability of finding this particle in this regime and in this regime? That is essentially 0, right? So because this psi star and psi is 0 for regime 1 and regime 3, the only condition we make this to be 0, this has to be also, psi has to be 0, right? Because psi star is just complex conjugate, right? So in the sense, this psi for regime 1 and then psi for regime 3, it has to be 0. Does that make sense? This one? Okay. So in the sense, technically we have to solve Schrödinger equation for regime 1 and regime 3, but we don't even have to, okay? Because, with this physical understanding, we already know the solution for regime 1 and regime 3, okay? Okay, so with that, again, just another implication of that is for regime 1 and regime 3, there is a 0 chance of finding this particle, right? Okay, so that is essentially kind of what this means, okay? So then what about for regime 2 or within the well or within the bucket, okay? So that is essentially we are going to look at now here, regime 2. So here we have to solve Schrödinger equation. So, let's apply this one. Minus h bar square over 2m d square psi dx square plus u psi equals e psi here, okay? So here, for this regime 2, the potential energy, okay, this U is essentially 0, right? Because this is essentially, the well is located, but at the bottom is like that, okay? Just like this description. So in the sense, for regime 2, this U potential constraint is 0, okay? So then, what we need to work on is simply minus h bar square over 2m d square psi dx square equals e psi. Okay. So, what is the solution form here? The solution form for this ordinary differential equation is essentially a times exponential minus I square root of 2me over h bar square e plus b times exponential I square root 2me over h square e. Sorry about this one, x, this one. Okay, this one has to be x. Okay, so this is the solution form. Okay. So for this one, this is going to kind of repeat over and over. So we are going to actually simplify this one. such that we are gonna introduce another parameter, this k square equals 2me over h bar square, or k equals, or this one is essentially k is square root 2me over h bar square. Okay, so I'm just kind of introducing just a variable just to simplify, and then we can actually replace this square root 2me over h bar square, or this one, with k. Okay, so what that means is that now this one will be, let me just kind of write down here. Okay, so what that means is that with this introduction, now this one becomes minus I kx plus b times exponential I kx. Okay, so this is the solution form for differential equation. If you look at it, there are two unknowns, right? A here and then B here. Okay, and actually, I mean, the K is also kind of unknown, but we are going to find that later. Okay, so here, like if you look at these unknowns, like how do we find? I mean, we have to find those unknowns, right? And how do we find them? Like when you are working with the differential equations. This one is now ordinary differential equations. Okay, so like now we just need to find these unknowns. In order to find unknowns for this space domain, we have to use boundary conditions, right? Boundary conditions. Okay, so then the question here is, okay, so what would be the boundary conditions? Okay, if you look at this problem. Boundary condition should be 0 and D, and then actually it's given here, right? It's essentially kind of boundary condition that we can work with. Okay. So, and then the generally boundary condition here we kind of often use is continuity of wave function psi. Okay, so for example, here the argument is that we have 0 and D, and we already know this has to be 0 and this has to be 0 in terms of psi. Does it make sense? That is a solution we got already. So here, whatever the value is, it can be kind of go crazy, but at the end it has to be continuous, right? So in the sense, this one has to be 0, and then here it has to be 0. Does that make sense? That is essentially kind of what boundary condition is. So in the sense, we are going to apply this boundary condition. We already actually have the equation here too. And then with that, we are going to use this psi x equals 0 equals 0, psi x equals D equals 0. Okay? So then we have two independent equations. So with these two independent equations, we should be able to find two unknowns, right? So that essentially, let's work on this first case, psi x equals 0. So, like what is the gas solution form? That is this part, right? This one. So we are putting x equals 0 here. So what that means is that now this one will give us a plus b equals 0, right? Because you look at this one here, x equals 0, this is 1, x equals 0, 1. A plus b must be 0. So from here, we know that b is negative a. And then the second case, okay, this psi x equals d is a 0. So from here, if we substitute x with x with d, that's minus I kd plus b times exponential I kd equals 0. Okay? And then here, we are gonna use again just the way I'm doing here is I'm just replacing x with a d, okay, and then the whole thing must be 0, so I'm setting 0. And then here I'm going to use Euler's formula in the sense that this is e to the ix equals cosine x plus I sine x, okay. So in the sense, I'm going to just express exponentials with cosine and sines. And with that, it becomes a cosine minus kd plus I sine kd plus b cosine kd plus I sine kd equals 0. Yeah. And then, this minus cosine, and then here, this one must be also minus here. Sorry about this one here. Sine minus I minus kd. Okay. Right. So here I'm gonna just re-express this cosine minus kd and sine minus kd to just positive. Okay, so for example here a cosine minus kd is essentially cosine kd, okay, and then sine minus kd is essentially minus I sine kd. Okay, we can express this way as well, and then the rest of them just follows. Okay. Okay, so then now we can kind of combine for like cosine and sine. So if we do that, now for cosine part, a plus b cosine kd, and then sine part plus I b minus a sine kd. Okay, so this is what we get. Here from first equation here, like first equation, we got this expression, right? B equals negative a. So what that means is that b equals negative a, and it turns out this term goes to 0, right? Because b is a negative a. And then this one has to be 0, right here. Okay, so and then this one, if I replace this b with negative a, now this one becomes minus 2ai sine kd equals 0. Okay. So from this equation, like what is the solution? What are the ways to make this to be 0? Okay, can A to be 0? Can A be 0? If A is 0, then what does that mean? Here we have this expression, right? If A is 0, B is negative A, that means it's a trivial solution, right? So so A cannot be 0, okay, because it's physically meaningless, right? So what that means is the only way to make this 0 for physically meaningful, this must be 0. Okay, because A cannot be 0, because if A is 0, B is 0, and it's nothing. Okay, it's a trivial solution. Okay, so in the sense here, if we look at this sine kd equals 0, so what that means is that now this one kd must be n pi. Okay, so here n can be 1, 2, 3, and so on, right? Because like if you actually look at the sine wave, it looks like this, and then there are many crossing points with 0, right? So this is essentially 1 pi, 2 pi, 3 pi, 4 pi, and keeps going on, right? So as long as we have this condition, the sign of KD is gonna be 0. Okay? Does that make sense here? Okay. So with that, remember what K was, okay? So this K, we actually introduce this variable, right? So K equals actually square root 2me over h bar square. Okay, so with that, let me just kind of write here, okay? Recall K equals square root 2me over h bar square. So with that, you just kind of plug it in, okay? So K is here. So I'm gonna just kind of replace it here. So if we do that, square root 2me over h bar square, d equals m pi. Okay? So what I'm doing here, just kind of replacing this K right here. And then with that, if I kind of rearrange this one, 2me over h bar square equals n square pi square over d square. And then here, remember, h bar equals h over 2 pi. Okay, this is a reduced Planck constant, just a reminder. And then if you just reorganize this one, h bar square over 2m n square pi square over d square, or this one will be 1 over 2m and h over 2d square. Okay, so here n is 1, 2, 3, and so on. Okay, so this is the energy of the particle sitting inside the well, okay, inside the infinite high well. Okay, so with this one, what does it tell you? Again, well, actually we saw this expression earlier, okay? Let me just kind of bring that in here. So this is actually the part we actually discussed before, okay? Do you remember standing wave that we discussed earlier? Okay, for standing wave discussion, and then when we use the matter wave, okay, this one is maybe matter wave. So in the sense that we are actually using this Dubrovsky wavelengths, okay, Dubrovsky wavelengths has a relationship like that, and also for discussion with the standing wave, we were able to get wavelengths expression. Do you remember? We were kind of arguing what is the longest wavelength that we can fit within the cavity, right? The next longest, etc. And then in the sense, this is actually wavelength expression we got for standing wave. And then we are using matter wave concept, and then when we kind of couple them for energy, this kinetic energy, then this is actually expression we get. Okay? So then look at this one. And the solution of the Schrödinger equation is exactly matched, right? So it actually gives us the same result, but also at the same time, when we think about the concept, okay? So what is the actually concept or the wave characteristic we are discussing for this particular example? Within this bucket or within this cavity, what kind of wave are we creating? It's a standing wave, right? Because essentially at both ends, we are essentially clamping it down, right? Because the amplitude of the wave at both ends is essentially what? 0, right? That is essentially we are replicating standing wave, and it turns out the energy expression is exactly same as, the standing wave and matter wave case before, okay? So in the sense, this is kind of another kind of evidence where, this Dubrovsky wavelength is actually like a very valid and acceptable, right? Because this one gives this result, and Schrödinger equation more rigorous way also gives the same result. Okay. So what does this mean? I think we actually discussed it before briefly. Again, for this particle, whatever that is, it can be actually small scale object or bulk scale object. The energy this particle can take has to obey this expression, and it turns out, if we actually follow that, when n is 1, because n can be only integers, energy is 1 over 2m h over 2d square, or n equals 2, n is 3. We can kind of describe the lowest 3 energy levels. We can actually describe these 3h over 2d square, and then so on, right? These are the 3 lowest energy levels the particle can take. Okay, so what that means is that when we actually express in terms of energy here, when n is 1 or n is 2, n is 3, this is the lowest energy, like ground level, and n is 2, and then n is 3. It's like that, right? The particle can take only energy levels like this, or and like if we keep increasing n, it's gonna go larger and larger, right? And what that means is that between these energy levels, this particle cannot take any energies here, right? Like here, this area, the particle cannot take any energies within this kind of highlight region. Does that make sense? Because like energy, the lowest energy it can take is here, and the next energy is here, and then the next energy level is right here. Okay. So what that means is that between these two, this particle cannot take this energy. Does it make sense? Have you guys heard about like band gap? Like in electronic device? Okay, this one is kind of similar to this concept. So, but anyways, my point here is that, okay, if you guys don't know, don't worry about it. Like we'll cover that later, okay? So here, the lowest energy you can take here, and then the next energy is here, right? So in that sense, if the particle, for example, cannot take this energy in this case, right? So the point here is that this energy level is discrete, or discontinuous. Okay. So this one is kind of maybe confusing because when we think about like a bulk scale object, right? Like within this the particle can take actually any energies. Okay, it can take any energies. It's not really discontinuous in terms of a bulk scale object. Okay, why is that? Actually, you can kind of find the answer from just looking at the expression. Okay, because what does it mean by being bulk scale object? Typically, mass is high, and also the well width is high, right? Then what happens? When mass goes up and the well width gets higher, that means we have delta E, energy difference is going lower. Does that make sense? Because as we increase M, as we increase D, this gap is gonna shrink. Does that make sense? Okay. And then when you think about this h, okay, h is actually very small value to begin with, right? So if we deal with just mass and d, well, with kind of bulk scale, this energy delta E is actually very, very, very small. Okay, so what does it mean? For bulk scale object, it's gonna look something like this. So when this object is actually very, very small, like electron, we have very large energy gap, but if we increase M and D, it's gonna be a little bit smaller. But for like a bulk scale object, it's essentially like it's kind of like very, very small. Okay, so what that means is that technically, when we really describe the energy distribution for bulk scale object, the energy level looks just like continuous. Okay, so for bulk scale object, like energy level is continuous, but for microscopic object like electrons, energy gap becomes wider and wider, and then there is apparent energy gap that we can notice and we can measure. Okay. Does it make sense here? Okay. So again, this energy expression, okay, this energy expression is universal, okay, whether the object is small or big, okay, but the like for small scale object, as I mentioned, this energy gap is apparent and then kind of obvious or like measurable. But for bulk scale object, this energy gap becomes so small such that energy level just looks like continuous. Okay. Okay, so this one is actually a very important concept in quantum mechanics. Okay, this is kind of discrete energy or discontinuous energy. This is a core concept, and we are gonna talk about this over and over. Okay. So that is one consequence of solving Schrödinger equation. Okay, and okay, so this is actually energy expression we got, okay, from solving Schrödinger equation, and then let's just kind of let's keep talking about this psi. Okay. So let us now focus on this wave function. Now, let me just kind of write down the generic expression. Okay, from here, by solving, boundary conditions, we already found that B equals negative A, and also K equals, or here, this one, KD equals n pi, right? This is the second solution we got. Okay, so let me just kind of write down. KD equals n pi, right? And then here is n is just integer. And then let's just kind of plug it in. Okay, if we do that, it's essentially psi equals minus 2ai sine kx. Here 2ai n pi over dx. Okay, this is what we get. Okay, and here I'm just replacing b here, and then k in terms of n pi over d. So then if you look at this one, like we still have one unknown here. Like the n is integers, d is the well width. So it's, in the sense, this is a physical parameter, but there is still have one unknown. Okay, so we will have to find out this unknown A. Okay, how are we gonna find that? We are gonna actually use the probability concept here, okay, to find this unknown. So the way we are gonna do is we are gonna use normalization. So what is the normalization? That is, when we consider probability density function, when we sum up all the probability in space domain, the value has to be 1, right? So that is essentially what we are going to use. For example, we are integrating over the entire domain, space domain X, and then what is a probability? That is a probability density function, right? This is a probability density function, and then when we integrate over the entire space domain, it must be 1, okay? Okay. So then when we do that, that is essentially negative infinity to 0, this psi star psi dx, and then here we have to separate into these 3 segments. Okay, this one is 1. Okay, so just notice, there are 3 segments here, right? So basically, this one is essentially the region 1, and then this is the region 2, and this is region 3, right? Because like what we are doing is we are essentially considering the probability for this region 1, and then this region 2 and region 3. Okay, because psi expression for region 1, region 2, region 3 are different. I mean, technically region 1 and region 3 same, but like we are essentially kind of separating into 3 domains. Okay, so once we do that, we already know what this value is, right? Because psi is 0 for the region 1. So in the sense, this one must be 0, and this one must be 0. Does that make sense? This one? Do you get that? Yeah, okay. So then we have to look at just the well part right here. Then once you do that, well, let me just kind of write down here. That is 0 to d psi star psi dx equals 1. Okay. So then we already know what psi is, right? That is essentially this part. And then we are going to just plug it in. Okay. So once you do that, let me see. This one, actually, like I have actually wrote down here. Okay, let us kind of go over this one because it's a little bit lengthy process. Okay, I just kind of prepared a note here. So we are going to use this argument. Okay, integration 0 to d psi star psi dx equals 1. And yes, here, okay, so this one is fine. But actually, one thing I kind of forgot to mention here is that when you look at this wave function solution, it has actually various expressions in the sense that n can take, any values, any integer values, right? So in the sense, like this wave function solution depends on n, because, n can be any integers. So that is why, I just want to make a note that here we often write down as n here, okay? Because, this n can be any integers, okay? N can be 1 or 2, 3, 4, 5, 6, 7, 8, okay? So this is why I'm just writing down as this wave function psi n, because it has n dependency. And with that, let's just kind of coming back here. So then when we plug it in, okay, what is a psi n? Okay, so for example here, psi n, here. Psi n is given as minus 2ai sine n pi over dx, right? I'm just kind of writing down here. And then we take complex conjugate. Okay, complex conjugate means, like we just kind of flip the sign for this complex number that is 2a star, because a we don't know, a is unknown. So a can be complex numbers still. Okay, so that's why, we take a complex conjugate for a. And then once you do that, like you just carry out this multiplication, that is 4 here, 2 times 2, and a star and a here, and then sine, we have the same term, so sine squared. Okay, and then we are going to use trigonometric identity here. Okay, sine squared is essentially 1 minus cosine 2x over 2, right? And then we are going to use this trigonometric identity, and then just replace this part with the cosine here. Okay. So once you do that, obviously this A star is constant, right? Unknown value, unknown constant, and then we can bring it out of the integration, and then you do integration. Okay. So you do integration here, then obviously 1 over 2 becomes x over 2, and then cosine becomes sine, and then you evaluate this sine term at d and also 0. Okay. So when you plug it in, d goes in there, sine 2n pi, obviously 0, right? And then when you plug it in, when you plug this 0 inside here, sine 0 is 0. So it turns out this whole term is a 0. Okay? So then the remaining part is only this one, right? So then once you do that, this is 4a star a d over 2, or 2a star a times d, this one must be 1 because of normalization, right? We are essentially using normalization condition here, 1 here, okay? So then once you solve this one, right? I mean, that is essentially a star a equals 1 over 2d. By the way, here there are two ways of making this equality, okay? A can be just real number, right? A can be real number, or A can be actual complex number here. Okay? So in the sense 1 over square root 2d or I over square root 2d. Okay? By the way, the solution that we kind of started with is this part, right? This one. And then here, I'm intentionally choosing this complex number solution because if I use this one, if I actually plug it in into A, it turns out it becomes kind of real number, right? This one becomes, because it has I, and then once you use this complex number solution for A, it turns out the final solution becomes kind of real number. Okay. But by the way, if you actually want to work with this one, like 1 over square 2d, that one is actually totally fine, totally acceptable. But if you use this solution and then get the final expression is going to be complex number, right? That's totally fine because, do you remember? This is a wave function, but what is a more physically meaningful parameter when we kind of interpret like quantum mechanics or Schrödinger equation? Physically more meaningful parameter is probability density function, right? Probability density function is what? Psi star psi, right? Psi star psi. So then, when you kind of work with just real number, psi star psi give you real number, but let's say you stick with this, and then you get the expression, let's say I here. When you evaluate psi star psi, it turns out what? Real number again. So in the sense, either using this one or this, when you finally get probability density function, the solution is going to be exactly same. Okay, it's going to give you the same interpretation in terms of probability. Does it make sense? Okay. Okay. So in the sense, this is the solution form. Okay. So with this one, let's just kind of go over that. Okay. Yeah. Okay. So what does this mean? Basically, like when we kind of express this one here. Just 1 second. Let me see. Yeah. So let me just describe a little bit here. Let me just give you the problem statement, okay? So we had infinitely high wall located at x equals 0 and x equals d. Okay, so in this sense, imagine we have bucket with infinite high wall, and then we are putting the particle inside the well. Okay, and then this solution is just for the region 2, right? Because the solution for region 1 was 0. This is essentially psi, okay, the wave function, and then we are describing psi outside. And inside here, you know, when n is 1, how do we describe that? You know, inside that is essentially this part, right? This is essentially when n is 1. And then when n is 2, it's going to look something like this. And when n is 3, I mean, it's a kind of bad shape. Yeah, look. Okay, this one is n is 3. Okay, you know probably what I mean by that. Okay, so basically, you know, like we are essentially creating several or like an infinite number of standing wave within that, right? So essentially, you know, that is actually a solution form for the region 2. Okay, so that's wave characteristics. So with that, you know, like let us kind of think about, my question here is, we are going to look at expectation value. Okay, so this wave function, or we can actually evaluate probability density function as well, because probability density function will be obtained by psi star and psi, right? But what that means is that, you know, there is a probability associated with, you know, finding particle matter, you know, at x. We want to find out, you know, what is the expectation value and uncertainty, okay? So in terms of what is the kind of average value of finding particle, you know, in this situation. So, you know, what is your guess? I mean, we are going to actually, you know, solve the problem. But what is your guess in terms of expectation value over average of position? Just by looking at the problem, okay? You're just kind of guess. What's your guess? Expectation or mean value or average value of position. Any guess? D over 2 is that is exactly at the center, right? D over 2. Okay, so you know, I mean, particle can exist between 0 and D, right? So, and then in terms of average, like at the center, or I mean, like you can take any guess, right? But that must be between 0 and D, right? So, but anyways, you know, like I mean, that's also reasonable guess, you know, like kind of saying that, okay, maybe in terms of mean or average, it may be exactly in the middle. Okay, so we are going to actually kind of go over that. Okay, so let's now get into that expectation of position x. So here, you know, I also kind of wrote a note here. Okay, let's look at this one. So how are we going to find expectation value of position? You know, this is exactly kind of what we cover. Like you have to use position operator, right? And then it turns out position operator is simply x, right? So I mean, you can kind of review the previous note here. So and then also in terms of expectation value, the way we express is, you know, like a bracket, right? X bracket. The way you do is you put position operator sandwich between psi n star and psi n, right? Wave function, and then integrate over the entire domain. Okay. And then again, because we have three distinct domains or regimes in terms of a wave function expression, we have to separate into three regimes, okay? First regime, negative infinity to 0, right? That is essentially this part. And then 0 to d, that is within the well. And then third regime is d to infinity, that is regime 3, okay? And it turns out, you know, this psi, right? This psi is a 0 here, right? Region 1 and region 3, and then region 1 and region 3 integration anyway is 0. Does that make sense? Okay. So what we really need to care about is just a region 2 here. Okay, 0 to d. So then you just kind of work out here. Okay, now psi n star and x and then psi n here. Okay. So then x position operator and then psi n, we finally obtain this solution, right? And then that is essentially this part, psi of n, okay? So you plug it in and then work it out, okay? So one thing actually I want to kind of mention here is that, you know, in order to find out this average or standard deviation, you must know this psi n, right? If you don't know this wave function solution, you cannot get this value at all, right? So, you know, like, I mean, it took a long time to get to this point, you know, but, you know, like, my point here is that in order to find out average value or uncertainty, you have to find the solution of Schrödinger equation for the given, you know, potential distribution, okay? But in this case, the potential distribution is very simple, right? Like x equals 0, infinity, x equals d, infinity, right? So anyways, with that, you know, this is a psi n and star. Okay, technically this is psi n star. But anyways, we are using real part. So, you know, like there is no complex number involved. So this is simply, you know, the same. Okay. So then here we have x and then sine square and then 2 over d, it actually comes out of the integration, right? So again, we use the trigonometric identity, okay? Sine square is simply 1 minus cosine 2a over 2. And then you kind of replace this part with that. And then this is what we get, right? And then, you know, this one has x. So if you actually put it in here, x over 2 minus x over 2 cosine 2n pi over dx, okay? So I mean, this one is easy to integrate. Well, it turns out this part has to be done using integration by parts. Okay? So integration by parts, as you know, this is a uv, is simply integration udv plus integration vdu. Okay, also integration udv here. Okay, this one uv is a udv plus vdu here. Oh no, actually this one is right. Oh, sorry about that. So, and then once you describe UV as like a UDV plus VDU, and then you kind of work out again, reorganize this one. Okay, so now integration UDV is simply UV minus integration VDU, right? So it's actually just coming from here. Okay, so integration UDV is a UV. Where did it go? UV minus integration VDU. Okay. So then you do integration by parts for this one. Okay, u is x over 2, and then dv is essentially cosine 2n pi over dx, and then you take derivative, and then you take integration, and then you do integration by parts, and then this is what we get. Okay, so then it turns out, you know, we evaluate x at d and then evaluate x at 0, right? So then it turns out the sine part or is essentially 0, and also when we work out this term, this is essentially sine becomes cosine, and then when we evaluate d and then 0, it's also 0. Okay. So then the end result here, X bracket is simply what? D over 2. Okay? When we actually go over, this lengthy process, the expectation value or mean of position is what? Right in the middle. Okay? So anyways, I'm gonna kind of describe this one in some schematic, tomorrow. But anyways, this is essentially like a rigorous way of getting the expectation value of the position for, this infinite high potential well. Okay, and yeah, that is it for today. And do you have any other questions?